As we want to build a quantum computer, we need to write programs. As we explained in previous lesson, we also need to have a microarchitecture which is responsible of the execution of the algorithm that one has written. Quantum algorithms from different application domains can be expressed in a high-level language such as the OpenQL language. In particular, we saw that these algorithms are composed of a mix of classical and quantum operations. The classical part can be executed on a classical processor, and the quantum part can be executed on the quantum processor. For instance, the Shor's algorithm is a famous quantum cryptography application for prime number factoring. This algorithm is composed of a classical computation, such as the greatest common divisor computation, and a quantum computation, such as the quantum Fourier transform. The initial human-readable program implementing the algorithm goes through different compilation steps, which produce binary code which can be executed by our quantum computer. The goal of the microarchitecture is to execute that code in a deterministic way and provide all the runtime support to execute both the quantum operation and the classical operation and provide back the computation result. When loading the executable in our microarchitecture, it is important to distinguish between those classical and quantum operation. For that, an arbiter unit is responsible for sorting those instructions to distinguish classical and quantum operation and route them to the appropriate pipeline. The classical instructions to the classical pipeline and the quantum instructions to the quantum pipeline. Those instructions are then decoded and executed either on the host processor or the quantum processor. One of the main tasks of the microarchitecture, or more specifically the quantum pipeline, is to translate those quantum instructions into analog signals which we send or apply to the qubits. These signals can be microwave pulses or constant voltages. So each quantum instruction is fetched from the instruction cache, decoded, pushed into the execution pipeline, and translated to an analog signal using a digital to analog converter. The digital quantum instruction need to be translated into a microcode instruction and ultimately translated in the right analog microwave.